Okay, this video is going to be the first video on section 2.5 on physical applications. So we're going to be talking about work. Work done by a constant force, so you can think of that as a push or pull. If an object is moved distance d in the direction of applied constant force F, then the work W done by the constant force is defined as work is equal to force times the distance. Or that could be work is equal to force times x, where x is going to be the distance traveled, or distance that the force moves the object. Okay, so work is equal to force times the distance x, and so our force could be in pounds, so pounds of force, and x would be in feet. And so our work here would be foot-pounds, or work is equal to force times x. X is the distance. Force would be in newtons, so we use the metric system, and x would be in meters, meters traveled. And so that force times distance would be newton meters, or that's also called a joule, or joules. Okay. And a newton is the force required to accelerate 1 kilogram of mass to 1 meter per second squared. Okay, and so we'll leave that to the physics class to get more into that, but let's go ahead and do a little bit of examples here. So work done by a variable force, and so we say if an object is moved along a straight line by continuously varying force, and we'll call that f of x, then the work W done by the force as the object is moved from x equals A to x equals B, is defined as the work equals the integral from A to B, f of x dx. So kind of get an idea, here's A and B, and depending on where we're at, we're going to be using a different amount of force. So maybe part of the way is on flat ground, and then we go uphill, so we're going to have to use more force of moving an object, and then going downhill, less force. So we're just going to look somewhere in the interval. And so there's the distance traveled, the delta xi, and a force of f of xi is traveled. So we have a little increment here. So in that little space there, our incremental work is going to be our force times the distance traveled. Okay, so then if we go through and we add up all these little incremental forces times their little pieces of distance traveled, then that's going to be approximately the work done. Now, if we let the the norm of the partition go to 0, and so we're taking very, very fine little tiny distances times the force there, that is going to give us the work there. So work is the limit as n goes to infinity, sum I equals 1 to n, f of xi, delta xi, and so that'll become the definite integral from A to B of f of x dx. Okay. All right. So let's go ahead and move along. We'll talk about mass density. So mass density formula of a one-dimensional object. Mass is density times the length of an object. So given a thin rod orientated along the x-axis over the interval, the closed interval AB, let rho of x, or you can think of it as p of x. We have the Greek letter rho that looks like a p, so you can call it p of x or rho of x, that's fine. Let rho of x denote the linear density function given the density of the rod at a point x in the interval. Then the mass of the rod is given by, the mass is the integral from A to B, okay, and density times dx, where dx is just a little tiny bit of a distance, okay. So mass is density times the length of the interval. So again, we can imagine a little partition, and we have little chunks of density times little chunks of length there, and we sum that all up and we get our mass. Okay. So last one here. Consider a thin rod orientated on the x-axis over the interval, closed interval, pi over 2 to pi. If the density of the rod is given by rho of x equals the sine of x, what is the mass of the rod? So mass is the integral from A to B of rho x dx. It's going to be the integral from pi over 2 to pi sine of x dx. That's going to be negative cosine of x evaluated from pi over 2 to pi. So it's going to be negative cosine of pi minus negative cosine of 0. I'm sorry, negative cosine of pi over 2. So it's going to be negative 1 plus a 0. So it's going to be positive 1. And that would be, in this case, we'll say it's in kilograms. Okay. So to get into some work problems, that'll be in the next video. And so we'll see you soon.